Welcome everybody to the start of our symposium, mini symposium on airborne wind energy.
So, as I said, I'm Jean-Baptiste Rismer from UC Louvain, and I will present you our work about large eddy simulation of airborne wind energy systems, and in this presentation mainly their weight. So, for the ones that are not familiar with the field, I may say AWES instead of airborne wind energy systems. Okay, so my presentation will be structured like this. So I will introduce some motivation, then continue with the methodology. Then in the result, I will present some wake analysis, then talk a bit about the force and end with the conclusion. So first, large eddy simulations are important as they allow high fidelity modeling of turbulence, and this is needed to study the AWES flight and wakes. So as for wind turbine, it is really important to understand how those devices will interact with the flow, how they will behave in turbulent and atmospheric flow, and also how they can interact with other structure waves. But it also allows to make evaluation of the unsteady loading that will happen on the wing and perform fatigue analysis. So I am using Ninos developed a large eddy simulation code developed at UC Louvain that use force order finite differences on staggered grid. And here in this work I'm using synthetic turbulence that is generated thanks to the Mann's algorithm. I will present you AWES flying different trajectories. So some of them I will call them optimal trajectories. They are generated thanks to AWEBox, that is an open source Python toolbox that generates those trajectories by solving optimal control problem that use here a simplified aerodynamic model. Okay, so within our flow solver, the wings are represented using actuator lines. The wing that I will model here is the MegaWES reference aircraft wing from TU Delft that has a wingspan of 42.5 meters and a surface of 150 square meters. So the trajectories will have a diameter of about 5 wingspan. My domain is 9 by 3 by 3 diameters, and I have 17 grid cells along the span, and we are making the simulation with a turbulence intensity of 6%. Okay, so the different cases that I investigated are the following. So we will have two circular trajectories, one that is orthogonal to the incoming flow, and the second one that is tilted at 37.2 degrees. It is depicted in the figure as in dotted. Then we have two optimal trajectories, one consisting of one loop, that is here, and another one that consists of 4 loops, and then the wheelout. So the major differences between the circular trajectories and the optimal one are one that the optimal have wheel-in and wheel-out phases that we do not have on the circular one, and also the circular trajectories have a constant rotational speed and also a constant wing angle with respect to the plane of rotation. Okay, so let us now jump to the results. So those are velocity deficits in the wake, in horizontal and in vertical, and horizontal plane. So when we can already see is that for the three tilted trajectories, that are the one that is circular and the two optimal one, we have the wake that is that will be deflected onwards, and that it mainly happens on the upper part of the wake. For the three tilted trajectories together, we can see that in the beginning they are quite different in the near wake, but as we move downstream, actually they become really similar between each other. And so here on a time averaged base, we can say that those wakes have indeed really similar velocity deficit. It is even more obvious on those two-dimensional velocity deficit. So here we can really well observe that the wake is indeed deflected, as it is for wind turbine actually, and that the three tilted trajectories are really looking similar. But now let us look at instantaneous velocity deficit in the wake. So the circular tilted trajectory and the one loop one are really looking similar, but now the difference comes when we look at the four loop optimal trajectory. So here, for the case of the four loop trajectory, actually the kite is moving downstream at a velocity that is close to the inflow velocity. So the tip vortices of the aircraft will merge between each other and create those stronger velocity zone than the one we have when flying only one loop optimal trajectory. And those high velocity zones are always released in the wake at the frequency of the trajectory. So, oops. So yeah, we have 4 times lower frequency here, and we can here really see an alternance of stronger velocity than lower, stronger, lower, and so on. So here I aligned 3D view of the vorticity intensity along with the velocity deficit, and it illustrates very well for the different cases the release of those stronger velocity and also highly turbulent zone that are released in the wake. Yeah. So now a little bit about the forces. So the optimal trajectories were generated with our box that also made a prediction about the forces. So here they are compared in the body axis reference frame against the one we obtain in the LES. So overall we can see that airbox tend to overestimate a bit the force in the y direction. So here it is similar to the lift, and slightly underestimates the force in the x direction. So that can be assimilated to the drag, and that we also see slight phase shift in the forces, but overall the agreement is satisfying. Okay, so we are coming to the end of my presentation. So we can conclude that our weights will really depend on the trajectory and also the characteristic of the trajectory, the power settings, angle of attack, and so on, and that we could have the influence in the wake that is also maybe a design parameter for the trajectory. Then we also saw that several loop trajectories tend, in our case, to induce stronger and lower frequency velocity variation in the wake. And finally, we have a quite good agreement with what was projected with our box. So the future step for my work will be to try to add the contour surface to this actuator line method and to move to a control aircraft rather than an imposed trajectory. And also we would like to investigate the feasibility of extending the framework to soft guide wings. So before finishing, I would just like to advertise a bit for the BORN project, which is a quite big project in airborne wind energy research that happens in Belgium. So in the next presentation, we will have Thomas from our group that will be talk about unsteady aircraft aerodynamic. Homid in the next session is talking about control, and then tomorrow Niels will talk about his simulation of wing resolved CFD simulation. So yeah, that's it for me. Thank you for listening. And are
there any questions? Just checking if the mic is working. I think that works, yes. Are there any questions?
I can just also speak loud. Thanks, Jean-Baptiste, for the really interesting presentation. Just maybe a couple of questions to understand better the results. So, what is the flying speed that you impose to the kite in the circular trajectory, and maybe also what is the turning radius compared to the wingspan? If you just
it's true that I did not wrote it on the slides. So the rotational speed is about 4.5 RPM. So it means that the time period is actually 14 seconds. Yeah, and so the diameter of the circular trajectory is 5 times the wingspan. So it means 212 meters.
Any other questions? Everything's clear?
Thank you for the presentation. You mentioned very quickly you used some turbulence in the beginning, right?
Yeah, the turbulence is modeled using synthetic turbulence generated with Mann's algorithm, so Manbox.
Okay, because, well, maybe I'm wrong, but I thought that was usually like it's on a specific instance in time you can generate like the power densities of the turbulent flow. I was wondering how you perceive that in time because you fly, or do you generate it for each position spatially?
I do not really understand where you want to go, but actually the Manbox is advected within the inflow. And so here the simulation are performed so that I have the whole Manbox that is 12 diameter long that move 2 times fully across the domain.
Okay, that was exactly what I wanted.
Okay.
Thanks.
Any other question?
Maybe just another, like, how much is deflected down the wing? Like, compared to you gave information about the tilt of the cone and like,
that's a good question. I didn't really quantify it, but it can be done.
Yeah, doesn't seem a lot, but yeah. So, okay.
Thank you. Then I think we need to move on to the next speaker. Thanks again.